Hello, welcome to our lecture 9, relationship between moment of a force and angular momentum. We're still in chapter 15. Should be 15.6 in your textbook. So we're again on the angular momentum, and we in previous class I talked about how a satellite moving in an angular path starts circulating the Earth, and it has an angular momentum. So in this lecture, our learning objective is to develop the relationship between moment of a force, which is force into distance multiplied by distance from where you want to take the moment, and then the angular momentum. So what's the relationship between those? Some application would be the same as our previous lecture 18, but I would like to give you one example of momentum application in real life. Is in a car. When we hit something, there's an airbag that comes out. So what the airbag is supposed to do? If we hit something, the car stops, and due to momentum, we jot out of our chair. Even though we have a seat belt, sometimes it'll save, but if it's so severe, it will not. So due to momentum, you'll jot or jump forward, and you will have a collision of your front of your the side of the car in front of you. The airbag supposed to inflate and increase the time for your momentum to get reduced. So your body gets more time to slow down your momentum, and the airbag gives that time, and that's how it saves us from severe injury when we have an accident. So let's start developing the relationship. So we're about to start doing relationship between moment of a force. You should already have an idea of what's moment of a force is from statics, and so moment of a force and angular momentum. Momentum angular momentum. So before we start finding or developing or formulating the relationship, let's talk about a scenario. We have x, y, and z coordinate. X, y, z coordinate, and we have any particle that is moving on a space. So not on a particular plane, but it's in a space. And for example, it has a path of this direction is moving. So currently the particle is at here. The red point is. And let's also assume that there's a lot of force or different force acting on the body. Could be F1, F2, F3. And let's assume that the resultant force of all the force is acting this way, summation of all force, right? Resultant force. And also let's consider the position vector from origin here to the particle is denoted by r, vector r, and this is our origin, O. So to develop the relationship, we need to start with our equation of motion that we have learned, F equals to ma. So since it's a resultant force, so we'll write summation of force equals to mass into acceleration, and we know that we can write the acceleration as a dv over dt, change of velocity with respect to time. And again, in shorter form, we can write the dv over dt as a v dot. Okay, so this is our first equation, equation 1. Now we're gonna take the moment of all the resultant force about any point, but for example here we're gonna take the moment from the origin O here. So the moment of the resultant force about point A. So the moment of all the force is we denote it by moment about point O, MO, is cross product of the vector position R, cross product with summation of all the forces, and it also has to be a vector. So the force, this resultant force acting in a direction, so it is also a vector. Yes. So now what we're gonna do in the next step, we'll look back to the previous equation, summation of force equals to, we see m v dot. So that's what we're gonna replace here. R equals to from here m v dot. So what it gives us, the momentum of O is with respect to O is R, and this is also vector, cross product of position R with mass into velocity. Now this is our equation 2, and then we're gonna talk, since we're looking for a relationship between moment, so this is our moment, we need a relationship with angular momentum. So let's find out our angular momentum. So our angular momentum is R. So angular momentum with respect to the origin O is the position vector R cross product with mass and velocity. This is also a vector. Now what we have to do is that take a derivative of this equation, the angular momentum. So if we take derivative, it will be d over h naught, and we're taking derivative with respect to time, dt. That gives us d over dt, and we're taking derivative of r cross product of mv. And the cross product would give us, you can look at the appendix B of your book, but we can for the cross product, the derivative of this cross product, the v is also vector, we can work it out is similar to applying the chain rule. When we have a multiplication and you do have to take derivative, you apply the chain rule. So if we kind of think of that way, if we take derivative of this term and keep this term constant, so what will be the first part? R dot, because we're taking the derivative of the R, and we kept the remaining part same, we're not touching that, so it will be m v. And what will be the second part? This time we keep R untouched, and we're going to be taking derivative of mv. Since m mass is constant, so we don't have to apply another chain rule on mv, because mass is constant. So it will be plus R, because R is untouched, R vector cross product, and this is also vector cross product m is constant, and derivative of v, so that we represented it by dot. So here what r dot means is d over dr over dt, and v dot means dv over dt, while v and r are vector. So you see, sometimes I'm writing the this mark, the vector mark, at the bottom or at the top here. Both is same, but you can follow only one, just marking the bar at the top or at the bottom, either one, making it so that we know it's a vector. So here I'm putting below, so it's a vector, and here I'm putting at the top, so it's still a vector. So this is our derivative of angular momentum, which is r dot cross product with mv plus r cross product with mv dot. So so we need to work a little bit on that. So again, we had from previous slide the first derivative of our angular momentum. We got r dot cross product mv, which is vector velocity, and this is also a vector, plus r, the vector, cross product mv dot vector, which is kind of acceleration. So now we have to concentrate on the second part, because we want to simplify any equation that can be simplified. So so this is the angular momentum has two terms. Actually, we're gonna focus on the first term here, which is r dot cross product mv. So we know we can write it as a r dot cross product equals to m. Instead of v, we can write dr over dt, right? Because velocity, our velocity here is the derivative of position with respect to time. So I write v as a derivative of r, which is vector, with respect to t. Again, the dr over dt can be written as r dot, because r dot means dr over dt. So it's exactly what happens. This term can be again written r dot cross product m r dot. Since m is constant, we can take the m out, so we can write this term as a m constant. We take the constant out and cross product of r dot with r dot. So we can, so one thing to notice, that if it was an algebraic form, even it's a multiplication, we can take the constant out. Even it's a cross product, we can take the constant outside, and then we can put the r dot cross product r dot in one side. So we know from vector that a cross product of the vector of the same vector is 0, because we know that the cross product, for example, if you have a cross product of a cross b, which is vector, now you get the, which is defined by ab sine theta, and n is the direction of that. So it depends on the theta, right? So if you're cross producting the same vector r prime cross product with r prime, which in this case both are vector, so the angle between the r dot and r dot theta equals to 0. So sine theta equals to 0. So that's how the cross product becomes 0, and that is why we are writing the r dot cross product r dot as a 0. So what it gives us, that the first term here does not exist. So this is 0. So we are left with h dot the angular momentum, first derivative of that is r dot r cross product with m v dot, first derivative of v. Now if we look back to our previous slide, that we have our equation 2. So if we compare with that, so we can get m dot, let me take a different, so we get from previous equation, we get m dot that was equals to r cross product m v dot. Now we see that is equals to h naught dot, so first derivative of h naught, which actually gives us h naught dot equals to summation of m moment. So this is the relationship between moment of a force and angular momentum, which tells us the resultant moment of or about any point. For example, here the origin, so any point O of all the forces acting on that particle is equal to the time rate of change of the particle's angular momentum about the same point, which was O. So this leads us to another formulation of equation, which is we know again from our equation of motion, is that summation of all force equals to ma, which is acceleration. If f is vector, then acceleration have a direction. So that can be written as m dv over dt. That's your acceleration, and we can take the m inside, so that will give us again d dt. So with respect to dt, and inside we will have m v. Because m was constant, we just put the constant inside the derivative, and that's not a problem. So when we take derivative of mv, it becomes and we represent the mv momentum as L, that we saw in our previous lectures. So if we represent mv with L, it becomes dl over dt, which actually gives you L dot. So the another equation we derive here is summation of all the force equals to first derivative of momentum. So the equation becomes summation of all force is equals to vector product first derivative of the momentum of that particle. So this is the another equation that we solve. So what that means is that the resultant force, all the resultant force acting on a particle or on a body is equal to the time rate of change of the particle's linear momentum. And this is another way we can represent Newton's second law. So let's move to the next slide. We're almost at the end of our this session, where we have to only we left with the talk. We have to talk about the system of particles. So we do this for almost every lecture. We derive the problem or formulate the equation for one particle, and we talk it about a whole body which contains a lot of particles. So let's draw an example. X, Y, Z, and we have a body here that has for example, a lot of particles inside. So let's take any particle. We call it this particle is I. Any particle, I could be any number, On that particle there is a force, external force acting. We call it a Fi because it's a particle I, and we take another force acting on that particle is a small Fi, that is internal force. And you know, from previous lectures we always cancel out the internal forces, but let's derive the formula for angular momentum. So the angular momentum, if we take the first derivative, and from previous slide we will have Ri cross product of the external force. This is for the external force, and for the internal force we will have another term, and that will be again Ri, the position of that particle, the ith particle, and cross product with the internal forces. So now for system of particles we will have two terms, one for external force, one for internal forces. But we also know that the internal forces occurring on a particle is equal and opposite to another particle touching each other. So the internal forces cancel out, and we can say internal force is 0 because internal forces cancel out. So we can simplify that H dot can be written only as Ri cross product of Fi. So it remains the same for system of particles. And so for the system of particles, angular momentum is R cross product with F, but it also this also represents the moment of force with respect to R, because we are multiplying force with the distance acting on that particle. So we can write for system of particles. Okay, when we're talking about system of particles, we have to put summation, because it's the summation of all the for all particles. We have to put summation on the angular momentum. So summation of all the angular momentum is actually the summation of all the particles R cross product F. Now this is a momentum of each of the particles because it's force multiplied by position. So we can write H dot equals to summation of all the moment. So this is the equation of system of particles, where we say this equation says as the sum of the moments about any point. For example, here from the origin, the position R, from about any point O of the external forces acting on a system of particle is equal to the time rate of change of the total angular momentum of the system about the same point, which is O. So so this is our equation for system of particles, and that was all about today, about relationship between moment of a force and angular momentum. So just a quick recap. So today we have formulated some relationship. The first relationship was for a particle, the summation of moment of all forces about any point O is equals to the first derivative of the angular momentum about that same point O. That was our first equation. Then we derived another relationship, that the summation of force is equals to the first derivative of momentum as L dot, and we had derived the relationship between for system of particles. So this is for only one particle, and for a system of particles we found that after cancelling out the internal forces, it's almost the same. M dot momentum of all the forces about the any point O equals to the momentum, the angular momentum, which with respect to the first derivative of angular momentum. So this is our second equation. So I think that is it for today. We will be solving problem in classes. See you in next lecture.